Hello, Wharton students. This is part 2 of the practice problem on bias-variance trade-off. Today, we're going to continue on the practice problems that we worked on last time. Fit the estimators of varying complexity, so from degree 1 to 15, using the training set for each data set. Then we have to calculate and plot the bias, variance, and error on the testing data set for each estimator, showing the trade-off between bias and variance with modal complexity. In order to solve this problem, we need to import some more modules. We need to first import pre-processing module to scale this properly. So I'm going to import pre-processing module, and I'm going to import linear models from linear regression. And I'm also going to import mean square error, the module that calculates mean square error. Let me reuse the function here, fx, that we defined earlier here. So we don't have to redefine it. And let's generate a large data set that is required here, from which large data set. So let x be the numbers between 0 to 10, and I'm going to make hundreds of them as x values. So these are going to be the x values, and the noise would be going to randomly generate this, not normal, from 0 to 0.3. I'm going to make them same number as x, so len x. And lastly, y is just equal to fx plus noise. So these are going to be the y values. Okay. Now let's sample a fixed test set of size 10. For this, let's generate test indices. So test indices, we can make it from random module, random choice, any number of x, this number of x with size 10. And we were not going to replace it. Okay, so let's generate test values. For this is for x, we're going to select the test indices that we randomly choose. So in 3 degrees, we're going to reshape it -1, right? And x test, this equals to test indices. Okay. Now let's create 100 different training sets of size 40 each to verify. So I'm going to make a placeholder for data sets. So we're going to do 100 times for, we are going to do this 100 times. The remaining indices that we haven't used, the indices that we haven't used are going to be, since we're not replacing it, we can just directly use this. So set difference, one dimension, and np dot a range, the number of x, and the test indices here. I'm gonna put test indices. Okay, looks good. And also for the training indices, we're going to make it randomly, random choice, remaining indices, and then size of 40, and we're not going to replace it. Train equals train indices, shape from 1 to 1, and y train also the same. For y, we don't have to reshape it because y is already 1D. And let's append that to the data set, our test train set. Oops. X train, let's say X train, okay. X train and Y train. Now we have to define our polynomial. So let's fit this regression. Definition of fit polynomial regression. So X, we have to take X and Y in degree as last time. And the polynomial features equals polynomial features for module. So degree, we're going to set degree and x polynomial. This one is the polynomial features that fit. Transform, we're going to transform the x values. Then let's place it, the model. Let's let the model be the linear regression as defined. And then I'm going to fit this model, x polynomial, and y. Return the model. This returns the model. Now we define the function to calculate metrics. So calculate metrics, we need models, big X, Y, and the true value of Y. So Y true. I don't see any. Okay, predictions. That is equal to np.array model.predict x. We have predict x for model and models. So those four models are polynomials that we defined earlier. So models and the average predictions, we use NumPy to calculate the mean of the prediction, and x is equal to 0. All right, and the squared bias is defined as the average prediction minus y true. So this is squared, so we need to square it. And the variance is we just directly use the variance function in NumPy. So variance of predictions, x is at 0. We use MSE for the error. So mean of predictions minus y true squared. This is x's, this is 0. Fix the spelling error. Average prediction. Okay. Predictions here. Okay. Now we have to return squared mean of the squared bias, mean of the variance, and the mean of error. So let's calculate metrics. So the maximum degree we have is 15. The bias, variances, and errors, we need to define the placeholder for these. These. And we have to loop it for degree in range 1 to maximum degree. Don't forget +1. So plus the models is the fit polynomial. We fitted the train values of x and train values of y, and degree for x train, y train, and data sets. It look great. Okay. All right, so this is the model that we defined. Let's create the test set for prediction. The test set x was polynomial features. So degree, we set it degree to degree because we were looping it. And fit, transform, x test, squared bias, variance, and error. And we use the function that we defined earlier to calculate metrics here. And then we're going to put models, x test polynomial, and y test. Then we're gonna put the bias into the placeholder into the array, bias array, append squared bias. Then the variances, append variance, and errors. Did I say errors? Okay, errors, append error. Nice. We have now, we set the degrees as a range. So this makes an array. So maximum degree, we're going to make an array of this. Let's finally plot this. So P of T dot figure, define the fixed size equal to 10, 6. Plot degrees and biases, and then put biases and plot degrees and variances. Then PLT dot, I'm going to plot the errors too. Plot. Okay, I'm going to plot the X label. So X label is the complexity. So we want to see the change of MSC, our error, as the polynomial degree changes. So the X label would be the model complexity. In other words, polynomial degree. The Y label would be the average of squared bias, also known as variance, also known as error. Our error, let's make a legend and let's plot a grid here. And lastly, let's see how it turned out. Okay, it seems like these three are so close together. So let me set the limit here. PLT, Y limit, 0 to 0.6 maybe. Let's wait. Okay, now I see the better picture here. You notice that the minimum error that we achieved here is about polynomial degree 8. So 8 is our best fit here. We can print the best model degree, best model error, and the variance like this. Thanks for watching the video. And if you have any questions, please drop them in the chat. Thank you.